So we will have today the pleasure to hear the presentation from Anna, which is focused towards zero-waste computing by co-design. So for those who do not know her, Anna is actually coming from Romania, from Bucharest, where she finished her bachelor and master studies, and then moved to Delft, TU Delft, where she continued as a postdoc researcher, and then at the University of Amsterdam as a tenure associate professor, as I remember. And now she's at the University of Twente as a full professor. Her research focus is primarily on high-performance computing and focuses on the aspects of modeling of the performance, modeling of the energy of the hardware that we have. That's why she has also quite a lot of experience, I would say, from also in industry, so visiting companies like NVIDIA, and I think now it's like the top company in the world, and then also Barcelona Supercomputing Center, and so on. So now it's my pleasure to introduce Anna, and Anna, please, you can start anytime.
Thank you very much. Thank you for the nice introduction. So I'm glad that NVIDIA is doing better after I left. But nevertheless, this is quite a while back. In the meantime, I've moved to this University of Twente in Enschede. And if you don't know where it is, I always like to joke that this is in the Netherlands borderline Germany. So that way is Germany. And we're literally borderline. So basically, it's like 10 minutes by bike to go to Germany. It's a small university. It's actually about 12,000 students and quite a lot of faculties. It's an engineering school, and it's really a nice environment and definitely a nice change for me as I moved there about 2.5 years ago. Good, but that's not what I want to talk about. So what I want to talk about today is this idea of zero-waste computing and what can we do to go towards zero-waste computing. The results I'm going to present are not only mine, but there's really collaboration work with a lot of my students. So you will see different results from different people. I will try to remember to mention their names if they're not on the slides. Good, without further ado, let's just dive in. So I don't think I have to convince anyone here that computing is everywhere and it's really not for free. A lot of the energy consumption that we see today is maybe a little bit hidden or not obvious, but really increases significantly with different types of computing that we're all using. So if you look at videos on YouTube, they are really significant in terms of energy consumption. If you look at things like AlphaZero, which is this kind of revolutionary way of solving gaming, this is also quite expensive in terms of energy consumption. You look at data centers, and a mid-sized data center can consume as much energy as a small town, and this is only the energy consumption for actual operation. In the Netherlands, the data centers can actually consume much more energy than the national railways, and trust me, the national railways are really, really busy and very, very overloaded anyway. So consumption is further increasing by these data centers. And in general, worldwide, it is predicted that our sector, so ICT, will reach about 21% of the global energy consumption by 2030. And 2030 is not that far away. So what I'm trying to say is that we are wasting, well, no, we are consuming a lot of energy in doing computing, different types of computing. All you see here is computing that we do or we benefit from. But this energy consumption is substantial and is constantly increasing. And the argument for today is, let us think what we can do to improve this, to actually try to make sure that the energy we consume is not necessarily less per se, because there's challenges in that as well, but that we can actually make the best we can from the energy that we're consuming. So the point is not necessarily to try to drastically reduce this energy, but make sure that we use it effectively. So how do we do this? Well, we identified 3 different types of stakeholders that can help us improve the energy efficiency in computing, or to reduce the waste in computing, namely developers and users. These are the people that actually do the programming and deployment of actual real applications. So I argue many of us here would be in this category. And for us, what we need to do is really make sure that we improve the energy efficiency of our own code and make sure that we design and implement the applications that can make use of the right resources for the right task. There's also system integrators, so we deploy our applications somewhere. We need to make sure that these will offer us the right mix of resources such that we can get the energy efficiency out of it and that we do get efficient hardware as the hardware progresses as well. Last but not least, we have the system operators, which are the ones that are actually scheduling workloads on system resources. So think cloud management, think data center job managers, and so forth. All of these things are really important in saving or in utilizing resources even better. So basically, harvesting energy where resources and systems are massively underutilized is part of the task of these system operators. Now, for the remainder of today, I'm going to focus on this part, mainly because this is where my work is. So I'm focusing more on the performance and improvement of energy efficiency of applications. But again, please keep in mind that this is a kind of a three-body problem, if I can mention it this way. So I'm going to focus on developers and users. So what I want to say really briefly, I want to give a few different views on performance and trying to bring in the point that high performance computing as we know it should make room for something else. I'm going to try to give a very brief definition of what I consider waste in computing, and then I'm going to give a few case studies for reducing such waste, examples of how we can do that, and then I'm going to try to summarize in this new definition of co-design, and if time permits, to show a little bit how we use this co-design into the EU project that we're collaborating in with Klagenfurt, namely Graph Massifizer. I will show you the take-home message no matter how many of the things in between I'm going to skip. Good, so let's just dive a little bit into performance metrics just to make sure that we're all on the same page. So traditionally, again, I've come from the world of high-performance computing. Traditionally, in high-performance computing, we do everything we can to get speed up. So basically getting the best performance we can, and we do that by saying, hey, we have a new version of an application, and we shall always measure the performance of the old version compared to the performance of the new version to get the speed up. The higher, the better, without any other considerations. Of course, we are moving now towards these new challenges, or we really need to start taking into account these new problems of efficiency. And efficiency at a very high level is defined as something like performance divided by the amount of resources. And it's clear now that if we get a lot of performance but utilizing too many resources, this becomes a problem because this leads to this concept of waste. Similarly, with efficiency, we talk about energy efficiency. And in this case, we're talking about the amount of performance we can get per the amount of energy we consume. Finally, there's this concept of utilization, and that really boils down to how efficient are we utilizing our resources. And my argument here is that we should take into account all these metrics when we approach a new solution or even new hardware, new systems and new applications together to actually solve our tasks. If we don't do this, if we keep going with the speed up part, we're going to continue wasting resources. And we see this on a regular basis in many of our high performance applications and machines. So let's say my point here is more or less that we move from high performance computing to high efficiency computing, and that doesn't necessarily mean we're losing performance, but it means we understand better how we are utilizing the resources at hand. So with this in mind, I'm going to, as I said, give a very high-level definition of waste in computing, and I'm going to say that unnecessary time or energy spent in inefficient computing is compute waste. So effectively, this gap between what we should be using and what we are actually using is actually compute waste. And to reduce it, we must really focus on efficiency to solution. So again, that doesn't mean to sacrifice performance, but it means we really need to strive for efficiency as much as we strive for performance. Good, hoping that I convince you a little bit how this looks like in terms of a very abstract definition. Let's try to make it a little bit more concrete. So let's just assume that computing waste is a consequence of underutilized resources. So therefore, look at this type of high-level model of our system and application. So assume we have two different systems, system 1, system 2, and we have the performance of the same algorithm and the same workload on these two systems. Now, assuming system 1 is larger than system 2, and by that I mean it has more resources, then we can define we can restate the same definition I said before in a strict form, saying that if the performance of these two systems is equal, however, this system is larger than this, then we have identified waste. Similarly, you can have a more relaxed definition. Namely, if the performance difference between the two is smaller than an acceptable threshold, then we have identified waste. It means that we have actually gotten not enough performance benefit by moving from system 2 to system 1. So how do we actually, what can we do about this? Well, first we should quantify this, so we should really understand whether there is waste in computing. And second, if we want to really tackle this, we can do more or less two or three things. Okay, more or less 2 or 3 things, that's a bit too much approximation. So we can basically try to improve the performance, either by improving the performance of the algorithm or by improving the workload in some form. So basically trying to push the performance up on performance 1 or on system 1, or we should really consider reducing system 1 to system 2. So it would be really important to understand that we have both opportunities. We are typically focusing on this side, but I'm arguing we have more and more opportunities here on these different types of systems to actually understand what systems we need before we deploy on whatever we have at hand. Okay, so I'm not going to claim this is easy. Definitely there are challenges in both efficiency and quantification, and improvement. And what I want to say today, I want to give you a few examples of how we can do this. I'm going to argue that reducing waste in computing, that's basically rehashing the point before, boils down to first raising awareness, which has to do with quantification, so monitoring efficiency and quantifying waste. And then it has to do with improving efficiency. And for that, we identified 3 different options. Either improving the applications for the systems at hand, improving the systems for the applications at hand, or co-designing applications at systems. I'm going to argue that a lot of performance optimization is going in improving applications for systems at hand. I think all of us have done this one way or another to get better speed up. There's a lot to do with multiple application sharing system, but I'm not going to focus on that today. We do have application-centric system design, even if we go and look back at things like reconfigurable hardware or in general system configurations. There's quite some work to be done here as well, but I would really hope that we can move on towards co-designing applications and systems. So really trying to make sure that we can combine the design of applications and systems early enough such that we can almost have zero waste by design. I'm also going to claim that a bunch of the things that we see on the top are solved by performance engineering, and this is a bit of a, how would you say, the advertisement for my own topic. So I just want to go and remind everyone that performance engineering, which used to be something a little bit like hacking, namely we have an application and we're going to spend a few good months to actually hack the best out of this and then finally get the performance that we're happy with. However, we have moved on from this towards, let's say, I don't think it's emerging anymore, but definitely towards a topic that gets more and more systematic and quantitative. So we're really looking into new methods and new tools to actually help us improve applications and systems by really a systematic process. So effectively, I'm going to simply say that performance engineering provides methods and tools to help performance-aware software design and development for most users. What does this mean? We need to evolve from what we are right now, namely using abstract models and hacky tools, towards more inclusive tooling and models that can be used for everyone. And I think we're definitely, sorry for that, we're definitely making progress in this direction, but I'm going to say we still have a bit of room to go. Good, I'm going to, so what do I mean by systematic? So performance engineering covers all these different aspects, from capturing requirements to analyzing feasibility to designing and implementing new algorithms, new solutions in general, maximizing code performance, and very importantly, documenting the results. And again, my claim is we do have tools and models that help us to do all these things. However, I will say that the integrated process is still a little bit far away from reach at this point in time. And of course, this is happening iteratively, so we need to do this over and over again. Good. So what are the challenges? Many of the methods you've seen in performance engineering are actually, or the steps that I mentioned about the process of performance engineering are actually very, there's still many ways or many things to do to improve them further. So we talk about understanding computer systems, we talk about defining performance standards, calibrating performance, using performance models, all these things where we have a good start in them. They're all necessary for performance engineering, but they are very far in terms of automation and generalization. So many of the things I'm going to show you now are things that we've done with a bit of an ad hoc approach, but we try to improve or to build the tools around them to actually create the performance engineering for all that I was mentioning. Good. So without further ado, let's just look a little bit at a few examples of how we actually do this performance engineering for improving or for reducing waste. And I'm going to first give you an example for category 1, improving applications for systems at hand. And I'm going to focus on graph processing. So why graph processing? Because graph processing is a very challenging application that appears more and more everywhere, because graphs are such a versatile data structure that we really want to try to use them in various applications for many types of analysis and prediction. Also, it is really, we really observe that we have larger and larger data sets that are getting more and more, that lead to more and more complex graphs. And we can't really say much about what happens when these applications get more complex or where the graph get more complex with the performance that we see. So the performance of these applications is notoriously difficult to predict. So whenever we had to handle applications that were more complex or they're growing in size and complexity, we threw parallel processing at it. So we had various types of parallel processes, be it CPUs, GPUs, or distributed systems, and we tried to solve graph processing on these systems. And we found that the problem of actually predicting the performance of this is actually very difficult, because graph processing inherently is not a parallel thing, and then trying to match this with the massively parallel architecture that we see today turned out to be an extra added challenge. So our goal with this particular research was to really understand whether we can adapt this parallelism, or whether we can find sufficient parallelism in graph processing for matching this with the newer parallel machines that we see. And that really meant, how do we actually find a good or the best possible algorithm for a given workload, and what is the right hardware for a workload? So these were really challenging questions. Actually, they're not yet solved for many of the algorithms we see. And we looked at this through a bunch of case studies. So again, the goal here is we have parallel hardware, we have massive graph processing, and we want to make sure that we find the best possible algorithm for a given workload. So we looked at BFS as one of the most challenging yet most easy to understand applications in terms of graph processing. And for those not familiar with it, what BFS does, it's a graph traversal that starts on a particular root node and goes and traverses the graph layer by layer. So this is all it does. There's virtually no compute in this application. It's mostly traversing data following these edges that you see in the graph. Okay, so how well does this application feature on a parallel machine or on a massively parallel machine? So we have identified a lot of different versions. So we actually had at some point about 20 different versions of BFS. In this work, in this presentation, I'm only going to show 8 versions, 6 of them that are based on different types of approaches, and 2 of them from related work focusing on a specific GPU optimization. So this is just an example of how these 8 different versions perform. So horizontal axis are the 9 different graphs we use for this research. Vertical axis is normalized runtime. What this means is that 100% is the worst case, so this is the worst runtime, and everything else is proportional. Different colors represent the 8 different algorithms. So what you observe, or what should be quite clear immediately, is that we don't have a best case that wins all the time. We don't have a worst case that loses all the time. And the difference in performance between the different cases can be significant. So we talk an order of magnitude or more performance loss by using the wrong algorithm. So clearly there is a need to understand what is the best algorithm for the given workload, because otherwise we are losing an order of magnitude performance by simply selecting almost at random, because we don't have no indication whatsoever from this from this type of analysis. So this is basically it. Different algorithms behave best, worst, and the performance gap can be significant. Good, so how are we going to do that? Well, coming from performance engineering, the idea would be we just take performance engineering for granted, and we're going to go ahead and do this. We're going to model the algorithm, we're going to calibrate to the platform at hand. In our case, it was a GPU, model the data set, we combine all of them together, and we come up either with a prediction for an execution time or a prediction for a rank. And by rank, I mean this is the best algorithm, this is the second best, this is the third best, and so forth. So that seems like a very good approach. And this basically, once we do this model, we're going to have all these predicted times or predicted ranks. We do the prediction itself. We plug in the platform and the graph parameters, and we pick the best version, and we're done. Well, of course, it is too good to be true. We do not have good enough ways to model the algorithms at the level of parallelism and at the complexity of GPUs. It's very hard to calibrate the platform, and modeling the data set remains an open question. We don't really know how to model graphs to the detail that we need for an application like that. So we tried all sorts of different models. We tried analytical models. We were really not able to go very far with it. We tried data-driven models. So by this, I'm calling them data-driven models. At the time, there's really very basic machine learning. So we looked at decision trees and random forest. These were the models that we looked at. We're looking again at predicting the execution time or predicting ranking. And we found, to our dismay, that the analytical model, as I was mentioning, was really low in terms of accuracy. However, the machine learning models were getting quite good in predicting in terms of accuracy. They were reasonably good, but they were also quite expensive in terms of prediction cost. And therefore, it was difficult to train them and to do the prediction significant. So the prediction was simply not good enough for getting this kind of best algorithm decision. Okay, so why was this the case? I have here a new graph. Horizontal axis now is the levels of one of the graphs you've seen before. This was I believe the number one in the previous graph. And vertical axis is now runtime. Still higher is worse, so lower is better. But now you observe that as we go, even for different levels inside the same BFS, different algorithms, these are the same algorithms as before, perform better or worse. So what we were trying to do was we got a model, and we were trying to predict an algorithm, best or worst, but that algorithm itself was actually a composition of these mini steps, these iterations going layer by layer in the graph, and at every step, one of the algorithms was significant, or some of the algorithms were really bad, and some of the algorithms were really good. So this means we were really having a prediction task that was too complicated for the models that we were choosing. So what we had to do instead was to actually try to predict the algorithms per layer, and then using this prediction, we wanted to construct by design the best possible BFS. So we had to predict at every level, not at the full graph level, because the granularity of the problem was too large for the models we tried. So what we did was actually constructed this best algorithm. So what you have here, again, horizontal axis is now the graphs, so the 9 different graphs that I showed before. Vertical axis is normalized runtime. What changed was we added this optimal. Optimal here is constructed as the sum of the best performance at every level. So if we would replace the best algorithm overall, or the algorithms overall, with a combination, for now it's a synthetic combination of the algorithms at every level, so the algorithms I showed you on the previous slide, we're going to get the best performance for each one of these systems. So clearly, the solution is not to try to predict the performance of one algorithm for the entire graph, but rather to change the graph at every level, change the algorithm at every level of the graph. So if we are able to predict the best algorithm per level, then we can actually construct by design the best possible algorithm. So we don't need to prove that anymore. We know it is constructed by design. So how do we go about this? Well, we need to predict the ranking. we need to construct this best algorithm. And then we basically created this mix and match framework where we build the best algorithm by switching to the best implementation at every level. So we're predicting at every level, depending on the input graph and on the platform, and we're combining these predictions by dynamically switching at runtime towards the best performing algorithm in every iteration. Okay, so we're able to do this with decision trees. So the analytical model was still inaccurate, but we were able to do this with decision trees, which turned out to be very good in both prediction time and in accuracy. You can skip this for now. So does it really work? This again is this is a performance analysis against the competing applications at the time. So what we have, horizontal axis are again the graphs, vertical axis again normalized runtime. And these here, Gunrock and Lone Star, are the, let's say, state-of-the-art best performing GPU implementations at the time. And what we see is mix and match. So this is our proposed solution, automated switching at runtime. Best node switching is what if we don't change the algorithm and keep it to the best possible algorithm at for every graph. And then the optimal one is basically the combination of mix and match. Sorry, it's the optimal one as you've seen before. So it's the perfect combination. It's as if you would have an oracle to tell you what is the perfect combination of graphs. Then this here is it. And what you basically, why did we include these two? This one here is to show how much you lose by not switching. And this one here is to show how much we lose due to overhead of dynamic prediction and switching algorithms. And you see indeed that the yellow one, the kind of ochre color, is often very close to the, it's very close to the optimal one, but it has this little overhead here and there. And we also see a couple of cases in which we are a little bit worse than the best known switching, and that is because in those algorithms there was no need for switching. So it was always one algorithm that was the best. So we were able to really demonstrate that we can do runtime switching efficiently without high overhead, and we were really able to show that on average we are faster than the state of the art by a factor of 3. So definitely we use this performance variability of BFS to do this dynamic switching at runtime, and therefore we were able to demonstrate that by by doing this design-driven approach, so we really designed the best possible BFS by this prediction, we could beat the state of the art. So what did we learn? We can indeed provide the faster algorithm by design. We can automate performance modeling using basic machine learning, but in the same time, prediction models are very difficult to build for data-dependent kernels, and we really had to do data-centric approaches. Analytical modeling failed because of very much complexity in the hardware, and this whole performance engineering approach and this training and collecting the data and training and everything took a lot of time and many gigabytes of data. So this really was a very big data problem, although it was a very simple algorithm and we looked at a few hundred of graphs. So basically, we ended up with a high efficiency algorithm. We had high occupancy for the compute cores, for the GPU in this case, but we've also seen low utilization of the compute cores because of the actual computation non-existent on the GPU, and high utilization of the bandwidth. So this here, the compute cores in this case, using a GPU for BFS is really a waste in compute resources, but we can't fix that because what we're after when using the GPU is the bandwidth. So we need the high bandwidth of the GPU, and therefore we had to sacrifice the computational resources. Good, so I want to also talk very briefly about energy harvesting on heterogeneous systems, and then I will go directly to co-design. So effectively, this is a different example. Now we're trying to improve the systems for the applications at hand. And the idea here is that we assume that we have this CPU plus GPU systems. And wherever we use this type of systems, different tasks run on different processors. So this means that if I have a task basically running on the GPU, the CPU might be idle and the other way around. Therefore, idle processors by definition will waste energy because they're staying there doing nothing. And we can try to do frequency lowering for these processors that are idle, therefore saving energy. This will be done with something like dynamic voltage and frequency scaling. Specifically, we focus on frequency scaling. And again, the idea was reduce the frequency of idle states and increase frequency when we have high utilization states. Here you have two examples. I'm not sure it's visible. We have two examples where we did a frequency sweep for the CPU and the GPU, and then you find that all the red dots, so you take the application as it is, you run it, you do a measurement, and now you do a frequency sweep. So you change the frequency on the CPU and on the GPU discretely for all possible versions, and then you see what do you get in terms of energy savings. So you see that you get some energy savings without losing performance in these green points. So there are frequency combinations that will give us similar performance but better energy efficiency. And for matrix multiply, these were more points than for something like k-means, which were just a few points. But the fact that they exist means there is an opportunity to actually try to harvest energy using this approach. So what we did for this was we created a small framework again to actually automate the analysis of an application, identify the phases and the utilization of the different processors, select and apply the right frequency based on these phases. And for this right frequency, we used a bunch of policies. So for example, high utilization means push the clock high. Low utilization means push the clock low, and things like that. So how did we do I think the most interesting part here was the states detection. So we were able to actually by monitoring the execution time of the application to detect these 5 different states. So the CPU idle, the GPU idle, or both idle, all of them are busy. And we identified this very unexpected CPU busy wait state, which turned out to be a side effect of a synchronization primitive on the GPU. So one synchronization primitive on the GPU would actually force the CPU to go into a busy wait state and consume a lot of energy. So we were able to detect these states at runtime, and we had the sampling rate or a checking rate of 10 milliseconds, but we can go up and down with this, but as low as 10 milliseconds was not a problem. So this is an example of what the output is. Horizontal axis is the timestamp execution of an application. In this case, is matrix multiply. So this is running matrix multiply. And different lanes, so to speak, are the different states identified automatically by the framework. So this is everything is idle. In this phase, the GPU is idle. Here, the CPU is idle. This is the busy wait, so massive synchronization, as you see. And then both devices being busy is here. And this is typically data transfer and some overlapping that was happening between the CPU and the GPU in terms of computation. So what did we do with this? Once we detect this, as I'm mentioning, we push the frequency up or down depending on the different states. And this is let's say a mirroring graph of the previous one, looking at monitoring the clock rate of the different devices. In red, the CPU, in green, the GPU. So you see that we kind of follow these phases and we push the frequency up and down, which leads to a significant change in the power consumption, which leads to potential energy savings. Here we have more lines because we did the measurements at the CPU as a whole and the GPU, at the CPU as a whole, CPU at the core level, at the node, the computational node as a whole, and for the GPU. So this is the GPU, this is the node as a whole. So this is really the energy that matters, the blue one. So once we were able to do this, but the question was, how do we exactly push the clock up and down? And we looked at different policies. I think the interesting part here is that there's a lot of room to improve these policies. For us, they were really trivial, simple things based on observing the states and nothing more. So what we wanted to do is to see whether these simple policies have any impact on our workloads. We looked at 10 different applications for different benchmarks, mostly from Rodinia and from NVIDIA's SDK. And we ran this on a GPU from NVIDIA with an AMD CPU. And I think, yes, this one. So what you see here are the applications on the rows. and then the best policy, namely the winning result in terms of a single core and multi-core application of our framework. And what you see in red are cases in which there is a decrease in performance, so the time has increased or the energy consumption has increased. And in green, what you see, or most likely you don't see, the cases in which we're actually gaining execution time and or energy. And you see that there's quite a varied picture. We have energy savings up to, I think, 28% or 26% here, but also performance loss up to 21% here. So that's definitely a very mixed picture. But we did identify cases in which the energy saving could be significant, and this would be without touching the application in any way. So this was completely on top of the existing application. So what did we learn from this? Well, there is a lot of high performance that is to be gained in heterogeneous computing, but there's also a significant energy consumption. Energy harvesting can work even with this type of tooling. Of course, there's quite a few challenges to still be explored here, namely, how do we explore this trade-off between energy and performance most importantly? And the question is, do we have a case for fixing the performance and looking for this one case in which the energy is a little bit better? Or maybe if we go into the direction of energy budget, can we just establish a fixed energy budget and use that for to maximize the performance within that energy budget? In this particular case, we actually reduced waste by frequency scaling. So this was an example in which we were able to reduce the waste in computing. Good. I think in the interest of time, I'm going to skip this. So this is an example that where we actually looked at shrinking the platform. Again, this is an example of improving the system for the application at hand, but really it is about being able to demonstrate what it would mean to create a different platform with different components and what would be the impact. There are different components. We reduce the different components on a platform and see what is the impact in performance and energy. So I can talk about this more if we have questions specifically. So I'm going to quickly skip this. Sorry for the for the animation I meant. I want to really mention very briefly this idea of co-designing systems and applications. So again, what I showed was we are pretty good at fixing a system and improving the application. We are getting better at understanding the application and building the system for it. Now the question is, can we do this together? Can we do this designing a little bit better? So ideally, what happens today, so ideally we want to go over what happens today with many of the applications. And I don't know if you see this, but I see this quite often. Again, coming from high performance computing, we have this traditional approach to high performance. When someone, a domain scientist, invents a new algorithm and a new application, they write a quick implementation. It used to be in MATLAB, now it's more Python than MATLAB, but they implement it, they run it, it works how it should be, and then they're benchmarking and it's slow. And in some cases it's as slow as they can't really get their paper in time. And then they call you, or they send an email, hey, I have this piece of code that is really slow, can you actually help me out? And then basically what they do, they send us a Python code or the MATLAB. We did have that, I am a little bit scarred by it. And we basically do this performance analysis, performance engineering loop over and over until we get a reasonable performance, and then we get back to them and say, here it is, now it's C++, good luck with that. So very often this is not sustainable, because there are cases in which we get a lot of these applications, and very, very challenging. The communication here is very hard, and this loop without the domain specialist in the loop is also very, very time consuming. So the idea would be, what if we can replace something like this with this concept of co-design, when we really want to combine this to push this discussion about the performance a lot earlier. And the idea would be, what if we can start the discussion about performance at application specification? So what if we can say, this application is built like this is what it's supposed to do, and then capture the functional requirements and the performance requirements together, and then come up with a design and a refinement loop like this that will allow us to already say something about the performance that we can get. So what if this thing is happening before we implement anything? Using performance prediction techniques, we should be able to do this and prune this space of the different possible designs to the point where we get a limited set that is reasonable, and from there we should be able to actually do automated code generation and potential tune it for the hardware at hand. So I'm not saying that this is trivial, and I think there's a lot of challenges to be tackled, especially in this part. But we know how to do this application design and performance analytics at design time. We know how to do code generation and tuning, and this would really help remove a lot of the overhead in creating a functionality, sending it further to the design, to the performance engineering, making sure that the performance engineer fixes something, and then doing that loop takes a lot more time than something like that. So this is what we're trying to do also in the Graph Massifizer project. I argue this is more sustainable, at least in human resources, if nothing else. And I think we should definitely go and try to do this, or at least think whether this is something possible in other places as well. As I mentioned, there are many open questions, so this is not yet a solved problem, but what we're doing in the Graph Massifizer project is we're trying to actually do this within the whole project. So basically, in Graph Massifizer, our task is in this box here, which is called Graph Optimizer, which really has to do with exactly this co-design approach. What we are trying to do is we're trying to build a specification of an algorithm from building blocks, predict the performance of each one of these building blocks and how they are composed, and then showing that we can come up with, similar to what I showed you for BFS, by design with the right combination of building blocks to actually create a best performing algorithm. So within Graph Massifizer, we call these BGOs, basic graph operations. Each one of them is a kind of a black box, and we can provide different implementations for each one of these BGOs. We can run them on different platforms, predict their performance, compose them into workflows, so we can put together algorithms or workflows combining these different building blocks, and then based on the performance models of the building blocks and the combination, we can actually say something about the performance before we generate the full application. And then we can actually generate the code by combining the code of the BGOs with this automated composition. So I'm going to skip this. So we are working actively on this. We actually have already an implementation for a simple multi-stage or multi-kernel graph algorithms, and we're doing quite well in terms of composition, but the results are still too preliminary for me to show to you. Okay, so just taking a big step back, we were talking about zero-waste computing, and I want to remind you that the whole idea here is to try to move as much as possible to high energy, high efficiency computing rather than high performance computing only. And we really have to take into account that this concept of energy consumption and energy efficiency is going to drive, or it is, I feel is the best way to handle the zero waste computing point. Reducing waste in computing is within reach. We can do that now with the techniques I gave you some examples of how this can be done, but I do think that co-designing applications and systems is the way to go, and this will really help us make significant reductions in especially in the underutilized systems that we use today. And then this co-design approach is something we are experimenting with in Graph Massifizer, and so far I have to say that we are quite happy with the results. So I'm going to leave you with this. So in order to really get to zero waste computing, we really need to do all of these things. We need to raise awareness to all our users. We need to really focus on efficiency as well. We need to take decisions at design time, and we really need to make sure that we take all the stakeholders on board. We can't do this on our own because we have too many applications and too few performance engineers. I'm stopping here. Thank you very much for listening.
Thank you very much, Anna, for the nice presentation. Now we start with questions. Klaus?
Yes, thanks very much for an interesting talk. Actually, I have a question to the second use case. Did I understand it correctly that you the assumption that you're making is that you have a system with a CPU and a GPU.
Correct.
And if the CPU is not really utilized, you consider that as a waste of resources, right?
Yes.
And the GPU is fully utilized, I guess, or not?
So we have these 5 different states in which you have. So we have a state in which the CPU is idle and the GPU is utilized, or the other way around. The GPU is idle, the CPU is utilized. We have cases in which they're both utilized and cases in which they're both idle.
Okay, but how do you define the priority of both components? Because I'm asking because in many situations I think I would prefer the situation where the CPU is idle and the GPU is fully utilized, because it's much better in a performance power draw ratio.
Absolutely, 100%. So the applications we looked at here are applications that are common using applications of GPU. So we looked at benchmarks and we looked at patterns that people have in applications where they use GPUs. So we did not touch the application. So clearly, if we would do better probably at, I don't know, overlapping computation and communication, or making sure that the GPU is utilized for more kernels, then we would definitely get better performance, and then keeping the GPU utilized for a long time would give us better performance and energy efficiency. So the point here was, if you have an application and you don't want to touch it, you don't want to change the CPU versus GPU utilization ratio, so you don't touch the algorithm, by simply observing what happens at runtime, you can reduce the energy of the resource that is not utilized, that is not being properly utilized.
All right.
So that's it's a fair point, and definitely if we can improve the algorithm, we should start there. This is basically just energy harvesting without having any insight into the algorithm or any foothold in the algorithm.
Other questions?
Thank you very much, Anna, for this exciting talk. I have a question on the co-design picture that you showed.
Yeah.
Looking at this picture naively, no, the other one?
Yeah, this one.
Yeah, looking at this picture naively, I would say there is no energy efficiency here.
Yes.
So you're just talking about performance engineering in co-designing with the functional requirements. Of course, after having heard your talk, the performance engineer will also take care of energy efficiency considerations. But how would this precisely come in here? Would this be additional requirements, energy efficiency requirements, and designing the applications such as to achieve load balancing, reduce memory traffic, stuff like that, in order to reduce resource usage?
So thank you for the question, and it's a very, very good point. I did not notice that I did. It's a really great point. So here, by performance requirements, I don't necessarily mean execution time, but I mean execution time and energy efficiency together. So that was the first point. So here, the goal would be to really try to have models that beforehand can predict what will happen. So I think if we get to the point of load balancing and memory accesses, either we were able to understand them in the moment we did the application design, or we will have to really. So these models here, this part here, these models have to be able to predict what will happen on a given device. So this is the loop where we should refine more and more the models that will give us the expected performance, and the final techniques, the tuning on load balancing and other things. If they were not captured here, then we will have to do it at this level. But I do think that what the performance and energy modeling should come into play already here, and this has to do with higher level decisions. I believe which type of GPU we should use. How should you partition the workload between CPU and GPU? When it's still efficient to use the CPU, although GPU will give you a better performance point, but because the CPU is idle, maybe you could use it. So it's more about the partitioning and about at the higher level of the application that gives us an envelope of performance where we can prune out the cases that are not going to be good. So all the bad ideas can be pruned out there, and then we come up with this streamline or a thin list of existing designs that should be already generated and tuned here. I don't think this will ever be one option. I think this would be a set of options. But I am confident that we can do this for both performance and energy, and I see them as alternative models right now. So we do have prediction models for energy, and we do have prediction models for performance. Sadly, they are very often well correlated, but luckily when we combine things together, performance, so execution time and energy are slightly different. So at least that gives us a little bit more excitement in terms of trade-offs.
Okay, thanks a lot. Big challenge ahead of you.
Thank you.
May I add one question?
Yes.
I was very interested in this mix and match approach and
Yes.
surprised that this works. How do you think about the generalizability of that approach?
That's also a very good question. So we're actually trying to do this, this is the wrong picture. So we're actually trying to do this by looking at at a bunch of other algorithms. Maybe I'll go here. So this works every time we have multiple algorithms that can be easily switched, and there's a significant caveat there. And every time we can actually combine them in an iterative manner. So what we need is so BFS, what is BFS? BFS is an iteration that for every level needs to do an update. So the question is, how do we do the parallelization at this every level? So this iteration is important. So if you have this iteration, this allows us to actually change the algorithm. So there's a natural point when we can change the algorithm. So I would say for every algorithm that is iterative, this works. The second condition is to be able to switch fast. So to switch fast, that means we can really switch the algorithm. So the prediction model has to be really quick. And then switching the algorithm has to allow that. And the caveat here is both the data structure and the data itself needs to be kind of portable between these different implementations. Otherwise, it doesn't work. And in our case, that's a little bit of an asterisk. Some of these data structures are vertex-based, or some of the algorithms are vertex-based, some of the algorithms are edge-based. And if we want to support that, so switching between them, which we do, we have to keep 2 copies of the data in memory. So we didn't go into data translations. It can be done. There's work that has looked into that before us, but for us, we didn't go into that. But you're right, there are specific cases in which this works, but we do hope this works for more algorithms. We're looking now in triangle counting. We know it works for PageRank, and we're hoping to look into, actually we looked at strongly connected components, and there we're also able to do, there's this step of pruning, and we were able to also do pruning with something like this, so decide which type of pruning needs to be done. But it's definitely algorithm by algorithm.
So many thanks, Anna, for very interesting talk. My question is about the first use case.
Mm-hmm.
Just as a general question, how did you find decision tree, performance of decision tree for the predictor better than other, machine learning predictors like XGBoost, random forest, blah, blah, blah?
So actually, we had previous work that, so thanks for the question. So first we looked at random forest because we had previous work that demonstrated that random forest is good at this type of prediction. So we wanted to use the same mechanism. Random forest worked, but it was really slow, and it was very hard to take the prediction and implement it within the C algorithm. So then we were looking for something simpler, and we found that the decision trees in this case, after a little bit of fiddling with exactly how the model is trained, we actually found that decision trees were very good in terms of predicting this, so they were good enough. We didn't need a random forest. One decision tree was good. And it was faster. We could embed it in our C code as well. And so the 20 milliseconds were really basically re-implementing the decision tree in C. So it was not using an external tool for inference. It was really re-implementing it inside.
So it's only applying machine learning techniques. It's not just dedicating it for this problem.
No, it was we just basically took a regular package, we trained the tree, we saw that the result was, it was good enough, and then we re-implemented it in C, but it was that tree, the tree that we trained. Yes, yeah, indeed.
And the second question is about the optimal definition. You talk about that somewhere for use case 1.
Yes.
But I just wondering to know, is it a standard tool, or is it common to define, optimal solution or optimal approach based on, this summation or
I think it's a very good question. We called it optimal by design, and the reason for that is we can take any implementation out there, we can put it through this framework, collect the data and include it, and then we can actually create a new version. So we can take any new algorithm into account to basically use to create this best or the optimal by design, meaning given the building blocks we have, this different implementation of BFS, we can optimally combine them to the sense that there is no better combination than this combination that we have. There's not to say this is the optimal BFS solution, because there might be a better algorithm out there that we're not aware of, but based on these building blocks, we were combining them in an optimal way. I'm hoping this answers the... Okay. But it's a valid question. I should be careful about what I mean.
Sorry, me again. I just want to understand one thing. You mentioned you utilized high bandwidth of GPU. What do you mean by that? Memory bandwidth?
Yes.
Or memory bandwidth?
Memory bandwidth,
Not
yes.
interconnect bandwidth to shuffle
No. This was a single node work. So we looked, but the point was that the reason for which the GPU was much better than the CPU was not the compute ability of the GPU, but the fact that it has a high bandwidth. So we kind of abused the machine only for its bandwidth. We did not use the compute cores at all.
Thank you for the presentation. About the BFS, as you explained, you are going at each level, select the best BFS algorithm implementation. By level, you mean breadth search? At each level of the breadth search.
Yes, yes, indeed. So when you go and you traverse the this is going to be forever. So when you go, and I cannot skip because my thing is not in a slide view here. So basically, this is a level. So at this level, when I need to go from this level and this level, I need to visit all the neighbors on the next level on this frontier, and this visit can be done in different ways depending on the graph representation and the algorithms that you choose.
And I mean that when the graph is larger and when you go down in the level, it grows exponentially. So finding the best algorithm might, it will be like more time consuming. Is it the case like for?
As the graph grows larger, actually the key aspect here is that this frontier can shrink and can expand and shrink dynamically. That depends on the topology of the graph. So if the graph grows larger, what happens is either the frontier is very large, and that makes the GPU very happy. So we couldn't find any graph that we couldn't fit a full level on the GPU. So GPU is very happy. The problem is when you get very narrow, and then you have a very, very poor utilization because you have just a few nodes that you need to visit. So actually, it wasn't harder to predict, but we knew that in some of these layers, the GPU is going to be very, very poorly utilized.
Okay.
So it didn't get harder with the larger graphs because we did this per level, and the number of algorithms was limited, so the decision tree was relatively small.
Yeah, just a quick follow-up question here, because you mentioned this is a big data problem. You collected gigabytes of evaluation data, but what actually was used here for the graph data? And how large were the graphs?
Yes, so we used about 250 graphs from the repositories, the Snap Connect. So these were the main repositories at the time. And we did 20 BFS searches for every graph, starting from 20 different routes. And we collected the performance of every traversal for every layer and the overall performance for each one of these 15 different algorithms. So it was really a lot, and this was the data that was used for training. So that's roughly it. Some of these things could be replaced with approximations, but at that time we didn't do that. We just went for measurements.
Yeah, thank you.
Sure.
Hi, thanks a lot for the interesting talk as well. As a natural devil's advocate, I have a few comments as well.
Thank you.
The one thing is, as far as I understood it, that to me at least, the talk has actually two main goals. The one is energy efficiency,
Yeah.
and the other one is energy saving. With one I do agree, with one I do agree less. First, but before I go into that, you said several times energy harvesting.
Yes.
I was a bit confused by the term. For me, energy harvesting is generating energy, not saving it.
Okay.
So I found the term a bit misleading, but just, I don't know, maybe other people see that term differently.
Yeah, so I mean, I can only say this. My experience with terminology in computer science in general is a very mixed one, so I think we're very bad at defining our terms uniquely. For this particular, so I'm just going to say this, for this particular work, we meant energy harvesting as kind of saving energy that is from resources that are not utilized. That was it. So clearly, I know that there are many definitions of, there are other definitions of harvesting. For us, it was just, we literally defined it because we had a similar comment before, whether this is harvesting or saving or efficiency, or so we just defined this is what we mean by harvesting.
I see.
Fair point.
It's just for me, harvesting is really just generating it, and
yeah.
And the second thing is, I'm very much keen on performance improvement. So in that sense, I totally agree. Well, the best case, of course, is just use a better programming language, like you said, C++ instead of Python. Mm-hmm. Or the other thing, which actually is supposed to be done in professional software development anyway, that you think first about the performance, because the best performance benefits you will always get with the better algorithm, like you showed here. And not by trying to fix it later when the algorithms are set in stone already, because then it's really hard to increase the performance. However, the main part that I have here is, and that's something that you will not be able to solve, is in real life, I'm not sure whether we see much of this when we save energy. We actually save energy in the sense that we just use more of it. So we just tackle larger computation problems.
Correct.
So in that sense, I totally agree with the performance benefits, and I think we should go that way. But the question is just, what's your take on how can we actually save energy and not just simply make things more efficient so we can do more of it? Like, if machine learning would be less efficient, then we simply would not use it much. So basically, I think it's really about the cost. And unless the costs are high, you will just use more of it. But what's your take on this?
No, I agree with you. So I think that's definitely the case, that as we see that we get more efficient at things, we're just going to keep using it, using more of those things. So that's 100% true. I think the answer of this is really understanding how we can... So I think the problem is there is a limit. So I don't think we will be able to do that forever. I think for many of the applications we see today, in data centers and things like that, people are really starting to look into, this is unacceptable to use a machine learning algorithm that uses 20% of our hardware. So this is just not okay. I mean, yes, it's efficient for you, but it's not efficient for us. And many of these data centers and many of the scientific computing I talked about is actually happening on things that are somehow not priced for us. So we don't get to pay the bill, it's the data center that does. But more and more data centers look into not giving core hours, but giving energy budgets. And this type of research is going to be very handy when that happens, at least for understanding what is the price that we have. So the point I'm making is that I think that on the one hand, you're right. We don't do enough of energy saving, but in the same time, I think we are also not giving people the tools that they can use to improve. So my point here is, let's build the tools that raise awareness, that allow people in machine learning that if they want tomorrow to make better use of the energy resources, they can. And I think we're not there yet. I think we don't have those tools for them tomorrow to decide, you know what, I'm going to use one GPU instead of two, because it's only 10% performance decrease, and this will save this much energy, and I can understand these numbers. And we're not there yet. We don't have those tools for them, and that means they can always say, yeah, we didn't know. But I think that's a serious issue, and machine learning is a very good example, because it's really one of the places in which energy efficiency is, I don't want to say ignored, but it's definitely put behind a lot of other priorities.
I can only totally agree with that, because in the end, in particular, I mean, in science it might be different, but in companies it's really about the cost of the development. And if you don't have the right tools for the development, then you will simply, well, I mean, it's the employee that's the most expensive part, not the software itself that is running, except for specific algorithms, of course. But in that sense, having the tools to make that easy for the developer is always the best way to go, I think.
Yeah.
So totally agree with that. Thank you.
Thank you. Thank you for the comments.
Thank you very much. Any other questions? If we have no questions, I have one short. I kept it for the end. From the figure that I noticed there, we include, according to me, almost all stakeholders. But I was wondering for one stakeholder, those were the hardware designers.
Yes.
Can we, in reality, include them? Because now as the time changes, at least that's my impression, take all these big monopolies like Amazon, Microsoft, they actually create their own hardware with their own CPUs, and then they optimize the hardware for the given problems that they have. And even companies like NVIDIA that provide to many different customers, they're still focused to neural networks. And actually even the hardware, like this latest Grace CPU and all of these are focused for that. First, can we include them here? And how the industry and the trends actually affect then high performance computing from scientific perspective?
So that's a really great question. So I moved from high performance computing into a group that has embedded systems in the title. So most of my colleagues are actually building systems. So yes, we can. However, the point is that this is a really difficult challenge. So actually, I think what I'm trying to say with this approach to co-design is actually that the building blocks we can use, we can still take the hardware that is given to us by companies and then build the right systems from that hardware. Of course, it would be great if we can convince them to actually tailor their processes for what we want, but we should be realistic. NVIDIA will never do that unless we are a multi-million or multi-billion market. But they did that for AI. So clearly, when there's an interesting application domain and when they were really shown the benefits, they were willing to kind of bend their design principles a little bit. Can we include them? I don't think we should rely on that just because the hardware processes are much harder. And again, we can do small hardware devices ourselves. We can look at the small scale. For big scale, for high performance computing, I don't think it is realistic to believe that we will ever have the impact to change the hardware. Again, I have a counterexample. So there is Fugaku. Fugaku is now in top 3 in the world for the last 4 or 5 years in terms of performance. And that is the machine that is purely co-designed. So what they did, they went and looked at all the scientific groups in Japan. They asked, what do you do? What do you do? What do you do? They extracted the requirements. They made a design of a processor that works for that. And they created a machine. But that is 1 out of top 500. Yeah. So will it ever happen again? Probably in Japan it will happen again because they know how to do it. Will it happen in Europe? We are trying. We're trying with ARM. So we're doing the best we can. And I think the EU is investing a lot. But we're not seeing anything revolutionary. Yeah. So, but I do think we see a bending in the hardware because of the performance of the software. So I think that's new anyway for the last 30 years. So I think we should be pleased with that. I don't include them here because I think that is a much slower process, and I think we can do it faster.
Yeah. Thank you very much, Anna, for the very nice presentation.
Thank you for the questions.